Hello, dear students. In the previous two lectures, we have derived a new definition of differential of a function at the point of the domain of the interval, and discussed that if a function is differentiable, that is continuous, but a function is continuous, that may or may not be differentiable at that point, and concluded that differentiability implies continuity, but continuity may or may not imply differentiability. Now, and proved the box theorem, and also proved the necessary and sufficient condition for a function to be differentiable at a point. Now we'll solve problem based on these concepts. The first problem is, let fx be a differentiable at a, then evaluate the limit x approaches to a of x square fx minus a square fx x minus a. Now taking left hand side, limit x approaches to a of x square fa minus a square fx upon x minus a. Change the limit from x approaches to a to x approaches to 0 after making the substitution. After changing the limit as 0, squaring x a minus a plus h whole square fa minus a square f of a plus h upon a plus h minus a. After simplification, squaring and multiplying them and dividing by h, we got is equal to limit h to 0 of h squares h fa 2ah upon h fa minus a squares into f of h minus f of a upon h. Now limit of the sums of limits, limit of this h equal to 0 is h, 0 is to 0, limit of this equal to a, the constant of h is equal to 2a fa minus a square, limit the h equal to 0 f of a plus h equal to minus f of h equal to 0 f h. After simplifying, we got u f a minus a square f h. Prove that fx is equal to x minus a has no derivative at x is equal to a. Now this model function, we have to discuss the left derivative at and right derivative at. So this is equal to given function, left hand derivative at a, f dash at a from negative or minus a from negative is equal to left hand derivative of f at a is equal to limit x equals to a from negative f x minus f upon x minus a. Change the limit or substitute value function fx and fa this limit, and now change the limit from x equals to a x, put x into a minus x x equal to 0 as x equals to minus x equals to 0. Change the limit from x equals to a from negative to x equals to 0. After this substitution, then cancel out the common factor and limit x equals to 0 of modulus or minus f upon h comes out to be minus of h upon h is equal to minus 1. Similarly, we'll find the right hand limit as x equals to a for positive, right hand derivative. Sorry. So f dash a for positive or right hand derivative of a is equal to limit a equal to 0 x equals to a for positive f x minus f minus a. Now substitute the value function at these values. Again, make substitution, change the limit from x equals to 0 to x equals to 0, and after simplification, we got this. Now, this is a question of limit. Here is a question of limit. After this question of limit x is to a from negative. question is given to be find the limit, then question starts from here. Differentiability, we reach at the for the differentiability at the point which is the count with the limit at the point. Substitution in the limit, we have discussed this question in the limit also. So limit x is 0 of a cancel this h upon h and mod h is equal to h is cancel this is 1. So left hand derivative at a is equal to right hand derivative at a. So this is not equal to is not equal to a is not equal to a, therefore not equal to a, therefore fx equal to x minus a is not differentiable at x. Now the question is fx is equal to x sine of 1 upon x sine 1 upon x is equal to x sine 1 upon x. Uh, if x is not equal to 0 and this is equal to and this is equal to 0 if x is equal to 0, then show that f is not derivable error or differentiable at x is equal to 0. Now again we have discussed the left limit or right limit because the function is same from left to right, so we'll find the left limit or right limit. And now we will see the different forms of the function of not if function is not continuous, function is not differentiable. So this question will prove the function is so that this is not variable means we'll find the left hand derivative of this. Limit x is to a from negative f h means f at 0 upon f means 0, limit x is 0 from negative x sine of 1 upon x minus 0 upon x. This comes out to be limit x is 0 from negative of sine of x. Now sine of this is does not limit of x which is 0 negative of sine of x does not exist. Limit x is 0. If you take the right, if find right hand limit, plus will be here, it will be here, plus will be here. Right hand limit of the sine of x does not exist. We proved it by Cauchy criteria. Cauchy criteria, this limit at x is 0 does not exist, implies this implies fx is equal to x. This function is not differentiable at x is equal to is not derivable or differentiable at x is equal to 0. I prove that the greatest integer function this function is not differentiable at x is equal to 1. Now again this is a x is equal to 1 is integer, so the integral values you have to find again both the limits, left limit and right limit, like left hand derivative and right hand derivative at 1. So f is going to be greatest integer less than equal to x. Left hand derivative of f at 1 is equal to limit of 1 from negative f minus f 1 upon x minus 0. Now change the limit from x equal to 1 from negative to x equal to 0. So substitute the value function and change the limit, and then limit the x equal to 0 to positive 1 minus h. This into function 1 minus h comes out to be 0, and this into 1 is equal to 1. H 1 will cancel upon minus h. Minus 1 cancel. This limit h is 0 1 upon h does not exist. So hence this is not differentiable at x0. You can also solve this problem by just by find latent derivative also. Latent derivative of 1 is equal to this is limit x to 0 or sorry latent derivative of 1 is equal to limit x goes to 1 from positive fx minus f1 upon x minus 1. Change the limit from x equals to 1 positive to x equals 0. Substitute the values of function at x equal to 1. Then change the limit x1 is equal to 1, 1 minus 1 upon h, and this is equal to limit of 0, 1 minus 1, 0 upon h, 0. So left hand derivative at x is equal to 1 does not exist, and right hand derivative is equal to 0 implies this is not differentiable at x equal to 1. Here this is equal to this, where fx is equal to this function less than equal to x. If a function is differentiable at a point, then fx is continuous at the point. But if a function is not continuous at a point, then the function will not be differentiable at points. So same problem can be discussed. Left hand limit at x is equal to 1 plus negative is 0. Right hand limit as x is equal to 1 from positive is equal to 1. Left hand limit is equal to 0. Right hand limit does not exist. Left hand limit is equal to right limit implies greatest singular function greatest function less than equal to x. At x is not continuous at x equal to 1 implies this is not continuous at this function less than equal to x is not differentiable at x equal to 1. Next problem is determine the set of all points where the function this is differentiable. Now, this function, the domain of this function are all real numbers because you can't be 0 at any value. If x equals 0, this will be equal to x upon 0 upon 1 is equal to 0. Doubtful point is because this is a point function, this is a constant function, this is your modulus function. Modulus function create the problem. So dot point is 0. So now let's extend modulus of x equal to x if x is greater than equal to 0 minus x if x is less than 0. Now add if x is greater than 0, then fx will be equal to x upon y plus x. If x is less than 0, then fx comes out to be x upon y plus x. Now we'll discuss the left hand derivative. Let's clearly fx is differentiable for x greater than 0 or x less than 0. Clearly fx is differentiable. Yes. Now let's find the left hand derivative. So left hand derivative at 0 is equal to limit x is 0 from negative fx minus f 0 from x to 0. Substitute the function at the fx and f 0. Simplify it and change the limit from x is 0 to x 0 from negative to f 0 to x equal to 0. After simplification to x 0 is equal to 1 0 0 is equal to x 0. 1 upon 1 minus h 1 minus h, this comes out to be 1 plus h is 0 is equal to 1 upon 0 limit is equal to 1. Similarly, write in derivative of fx at x is 0 from positive limit x equal to 0 from positive fx minus f 0 from x minus 0, this is equal to limit x equal to 0 from positive. So substitute the value function and simplify them. We come to the we come to that f limit becomes limit x is 0 from positive of 1 upon minus x and change the limit to 0. Again find the limit. So limit x is 0 of 1 upon 1 plus h plus x is equal to 1. So left hand limit is equal to 1, right hand is equal to 4. Left hand derivative at x is 0 is equal to 1, the right hand derivative at x is 0 is 1. Therefore, f is differentiable at 0, 0. So implies f is differentiable for all values of the domain of function. For what choice of a and b is the function f is equal to x square if x is less than equal to c, and ax plus b if x is greater than c is differentiable at c. For what will it be? So now differential at c. So how to problem this problem? This is some technical problems. We have two unknowns. In order to solve two unknowns, we must have two equations. So we'll use the concept of give given is fx is differentiable at c. Therefore, at a contrary c, that is limit x is to c from negative, fx is equal to c plus positive, f is equal to fc. F is continuous at c. Differential c, continuous at c. We get one equation. F is differential c, left hand derivative at c is equal to right hand derivative c. The two equations, we get two simultaneous equations a and b and we can solve it. So left hand derivative c function is left x square, right is ax plus b and c is equal to c. So from this we get the equation ac plus b is equal to c square, one equation. Now since f is differential c, so left hand derivative at c is equal to limit x is to c from negative, fx is minus f minus a is equal to limit x is to c from positive, fx minus f. So now substitute the value function, cancel out the common factor. Now, now after substitution, we got the this problem limits line. Concepts of limit will be applied when we have substituted the value of function in the derivative, left hand derivative as well as right hand derivative. So cancel out the common factor or change the limit. change that we can cancel out the complete. We can find this by cancelling the cancel out constructor or by changing the limits. Limits, substitute the limit from x is 0 to x is 0 both sides, and then simplifying them, cancel out the constructors, and this is equal to make the substitution, which will find the continuity here, and we have made substitution because AC plus B comes out to C square. B AC plus B comes out to be C square. C square C square cancel. This will become limit x 0 of minus h plus 2c is equal to limit x 0 of ah upon h. H is cancel. This is equal to a. This is equal to x is 0. C is a constant. Limit of c is equal to c. Limit of 0 is equal to 0. 2c is equal to a, and implies a is equal to c. Substitute the value of a to c in the equation first. AC for b to c square. We got the value of b equal to minus c square. The choice of a b for the function is this function is differentiable. This function is differentiable at the point is a must equal to c and b must equal to c square. Now next problem is, for what choice of a and b is this function f is equal to x square plus 3x plus a, like x is equal to a, bx plus 2 or x is differentiable. Again the same problem, fx equal function for x is polynomial is less than equal to 1, fx is equal to this polynomial for x is equal to 1, and fx is equal to this polynomial for x is less than 1 is differentiable. So again, two unknowns, we did two equations, so differentiability at a implies quantity a in function space, differentiability at 1 implies quantity at 1, quantity function quantity at 1, left limit at 1 is equal to right limit at 1 is equal to very function. So from this we get a equation x is equal to negative, function is equal to negative is equal to bx plus 2, limit x is equal to negative, is equal to x positive, is equal to x plus 3x plus a, and is equal to at 3 is equal to at 1 is equal to 1 plus 3 plus a 4. So now limit the following function, where whether you change the limit from x1 from negative to x0, you get the same result because polynomial you get this equilibrium. The left limit and right limit is equal to 1 equals to right 1 1 is equal to 1 plus 3 plus 4. So we got equation b plus 2 is equal to 4 plus a. First one equation is equal to b is equal to b plus b minus. Similarly, since given is fx is differential rate point, so left hand derivative, right hand derivative, definition, left hand derivative, and substitute the value of function at x is equal to, so after substitution, simplify them, cancel out the common factor, and cancel out the common factor, and then make a substitution, the factor, then make a substitution, and a is equal to b minus 2 equal to b minus 2 equal to b minus 2, and cancel the constructor. This is equal to minus limit x is 0, limit 0 is here, hx cancel out, 5 there will be limit to be equal to x, so minus b is equal to limit of this 0 limit of 5 constant is minus 5, so b is equal to 5, and substitute the a b is equal to 5 minus b is equal to b minus 2.